Welcome back from spring break. So today we're getting to what I think is sort of the end of a lot of hard work. The first half of the semester we put a lot of effort into giving ourselves a bunch of building blocks for building digital systems. And then recently we've been talking about an instruction set for a computer and trying to convince ourselves that we had all the instructions that were necessary to compile high-level programs, high-level language programs into machine code. And I think with the conclusion of sort of doing procedure call and return and getting all the conventions straight about who says what registers and where arguments go and things like that, we're finally all set to actually say, okay, we have an instruction set. We want to implement it. So, here we are at sort of one of the, I think, the highlights of the course where we're finally going to put all these separate storylines together and work on a circuit diagram for a computer today. Whenever you're doing a digital design, you have to think a little bit about what your goals are. And in addition to functionality, in other words, achieving, making sure in our particular case that we can execute all the different instructions in our instruction set, that the hardware has all the capabilities needed to do that, we also might want to ask ourselves some questions about what other goals would a design achieve. And the typical sort of conversation that happens in engineering teams, we first talk about, trying to build something that has high performance. And sometimes the goal is just the best performance possible. If you're into sort of the supercomputer game, every time you can make your computer faster by a factor of 2, you're really pleased with yourself and you move up higher in the rankings and more people buy your machines. In a different dimension, and this is becoming increasingly important, is sort of minimal cost. As we embed computers in pretty much every component, particularly electrical components that have any sort of functionality, some sort of sequencing they have to go through, and whether it's washing machines or refrigerators or desktop computers or satellites we're sending out of the solar system, those all require some amount of intelligent control, the control that reacts to sensor data and controls the actuators correctly. And often, particularly if we're trying to computerize a light switch or something like that, we'd be very interested in doing that at absolutely minimal cost. We don't want to have our interface of a device, of a component to the digital world to be very costly. So we're hoping to spend, on the order of maybe cents even in trying to make that happen. And then finally, there's sort of the middle ground, and that's the ground we'll be taking today. And in fact, we'll be spending most of our time just making sure we have the functionality correct. But when you work on the design project at the end of the course and take your functional beta design, which you'll complete for Lab 6, and work on trying to make it better, you'll be working against a sort of a benchmark metric, which sort of combines both performance and size. So we'll be looking to reduce the size of the circuit where we can, and also to make it perform as well as we can. Take some of the slow paths and speed them up so that our circuit can clock at a higher rate. When designing, in particular, a digital system that emulates in hardware a computer instruction set, here's the sort of the pieces of the formula that go into determining the computer's performance. So, we're going to measure the performance of the machine in terms of the number of instructions per second that it completes. Nowadays, the sort of computers that we have, in our pocket probably are several hundred million instructions per second they can complete, and then sitting in front of us in our laptop, maybe a billion or 2 instructions per second that it can complete. And maybe in a supercomputer center several times that. Some nowadays with these fancy graphics cards that have hundreds and hundreds of functional units in them, they may be completing a billion or not a billion, a trillion or 2 instructions per second, mostly through parallelism. So our goal here is to sort of say, look, first of all, we're going to design a machine that will execute 1 instruction every clock cycle. In other words, the machine will have some registers in it that hold the state, And so it's a sort of our typical diagram of some logic and some state registers. And we're going to clock those registers at some rate. And every time we do rising edge of a clock, we'll mark the end of the current instruction and the beginning of the next instruction. So we're going to design a machine that does one instruction every clock cycle. And we're able to do that because we have a very simple instruction set, a reduced instruction set computer. That's what the beta is, a RISC machine. And then we're going to try to get the best performance as possible, although we're not going to spend a lot of time on that today. Right at the end of the course, we'll come back and we'll talk about increasing the clock rate by taking our big, single stage pipeline stage, a single sort of our fancy finite state machine with logic and a set of registers, and worry about pipelining it so we can get the throughput up. And the machines that you have in front of you in your laptops, have a 20-some-odd stage pipeline that they're executing instructions in. So their clock rate is, about 20 times what they'd be able to achieve if they didn't use the pipeline at all. And that's part what makes your computer so fast. Okay, so let's think about what it's going to take to actually build a hardware emulator for the beta instruction set. Well, the key to figuring out what an instruction does is shown here. Here's the 32-bit instruction word that we'll be fetching from the memory, which will hold both instructions and data. And it's the high order 6 bits of the opcode that completely determine the format of the remaining fields of the instruction, and then what operation is to be performed. So our hardware will certainly look at the high order 6 bits of each instruction to determine what the operation is that we need to do. We actually have 2 different formats of instructions, one of which involves 2 register operands. So remember, we have a 32 element register file. There's 32 registers, each of which holds 32 bits. So it's a little array of these 32-bit locations, and there's 32 elements in the array. And we can basically reference 2 elements of the array, the RA register and the RB register. And then we can choose to write our result back into a 3rd element. So that's one format of instruction. We have a second format of instruction which is very similar, except that the second operand, instead of coming from the RB register, will actually come from be a constant that will be built from part of the bits of the instruction itself. And I'll say more about that in a second. So with these operate class instructions, we can specify a large number of arithmetic and Boolean and comparison operations, plus some shifts. And they all basically take 2 32-bit operands and produce a 32-bit result, which gets written into the RC field. In addition to the operate class instructions, we have a bunch of sort of, I don't want to call them miscellaneous, because they don't involve a numeric operation. But they really round out the capabilities of our machine. They let us load information to and from main memory and the registers. So that's load and store. And then there's 3 instructions, jump, branch equal, and branch not equal, that let us change where the next instruction comes from in memory. Normally we're just fetching instructions sequentially from memory, but we can change that with the jump and branch instructions. And finally, there's sort of a weird instruction called LDR that you'll talk more about in a section. Our approach for building the machine is going to be very straightforward. We're simply going to take a napkin, in this case a PowerPoint slide, and start drawing a data path, a collection of registers and multiplexers and memories. And we'll just keep adding features to that data path until we've come up with enough hardware to execute all of our instructions. You'll see that actually the schematic diagram, which is what's here at the top of the page in your unpipelined beta diagram, so this is the diagram we're going to be developing incrementally, is actually very simple as circuit diagrams go. It only has a few components and they're wired up in a particularly straightforward way. I would encourage you to, to sort of try to follow along and imagine if you were stuck in a room and had to, completely recreate this design from scratch. That's the sort of thought experiment I hope that you'll be running as we go through today's lecture, and say, look, I will watch Chris do it this time, and next time I'd be able to do it from scratch. If you can do that, then I think you probably understand how to build these sorts of diagrams. Okay, so we're going to sort of go through the instruction set sort of group by group and build our machine. Our bag of components, we're going to have these registers, all of which will be pretty much 32-bit registers. So they take a clock, and on the rising edge of the clock, they load a new value into the register. We'll use multiplexers, and again, mostly they'll be 32-bit multiplexers. In other words, the data coming into them will be two 32-bit words, and we'll get out a 32-bit word. This is a 2-to-1 multiplexer on the slide here. You'll see that we actually have other multiplexers. We have a 4-to-1 multiplexer and an 8-to-1 multiplexer. So all of which really, the multiplexers are a way of steering data around the data path. And you'll see that they're very handy for doing that. We have the ALU that you designed as part of Lab 3, which does all the heavy lifting of actually doing the arithmetic and logic operations. That's what ALU stands for, right? Arithmetic and logic unit. Also some shifts and some compares. And you've already done that design. Thank you. And then finally some memories, and I'll talk more about the memories as they come up. Okay, so the first memory that we're going to deal with is our magic little array of these 32 scratch pad registers. They're placed where almost all the instructions get their operands and write their results. So we actually have this little group of 32 registers. Each one of these little rectangular boxes is a 32-bit register. It can hold 32 bits of information. So these heavy lines here are actually 32 signal wires all coming in this case, to this particular register. We supply two addresses, if you want to call them that, or select lines, one of which will select information from any one of the 32 registers and provide it, give that value, that 32-bit value, on the read port down here, the A port. And again, we have a different set of address wires that independently selects any one of the 32-bit values to the second read port. So the two read ports are completely independent. They can read the same register, they can read different registers, depending on what the A cell and B cell signals are. How many bits wide is the A cell signal? It has to select one of 32 registers, so how many bits should we be sending in? We should be sending in 5 bits, right? Because it takes 2 to the 5th. With 5 bits, we can specify the 32 possible combinations of addresses that would let us select which one of the 32 registers we're reading. There's also a destination, a 5-bit destination number that is used. This is a decoder here. So given a 5-bit number here, only one of the 32 output lines will be on, and it controls which one of the registers will be written at the next rising edge of the clock. And just to remind ourselves, a clock-enabled register, that's what this little EN is supposed to signify, the enable signal. When the enable signal is high, the register will be loaded with whatever's coming in on the D wires. And if the enable signal is low, the register is loaded simply with its old value. So you can say, well, why don't we just do something fancy with a clock, do some logic so that the rising clock edge doesn't happen. And that turns out to be fraught with danger as you get down to low-level circuit design. And it turns out that this little diagram here, which involves this little 1-bit multiplexer, is a much safer way of implementing clock-enabled registers. And so almost all designs that I know of do that. The trouble with using logic to do clock gating is that any sort of little glitch in the logic will might produce an accidental clock edge, and the register might clock accidentally. As you change the values on the enable signal, you don't want all of a sudden a clock edge to be produced. And so this way, the clock goes directly to the registers, and we're using the enable signal to control what the registers will load. We're going to package this up into a single module, which we call a 3-port register file. So the register file is the name for this little 32-bit scratch pad memory that has 32 entries in it. So we send in 2 5-bit read addresses, and some amount of time later, it's what's called a combinational read port. No clocks involved. TPD, after the addresses become stable, we get the information out of the register file down here on the RD1 port and the RD2 port. So we're reading 2 separate registers out into the 2 data ports here. And then we can also supply a write address and some write data, and a signal that, by the way, says, I want you to write. So if we don't want to write at all, we can turn off that write signal. we can use the write enable to say, ignore the write address and the write data, don't do any writes at all. So that's sort of like another control signal that says that 32 to 1 decoder that we had, or the 5 to 32 decoder we had that selected which enable signal to produce, to enable to write into the register, to pick a register to write into, we can just disable that logic altogether. I'll say more about that in a second too. And then the write happens at the rising edge of the clock. So this is really just like a register. The writes happen at the rising edge of the clock. Which register gets changed, if any, is determined by the address wires and the enable wires. And what the new data will be is determined by the write data wires. Here's a timing diagram of how the register file works. And these are the sort of things you see in data sheets all the time when you buy digital components. These are the sort of timing diagrams that you have to sort of learn to read. What this one is telling me is that a certain length of time, so this number is, in the case of our beta, about a couple nanoseconds. After we have a stable read address, we will get the appropriate data out of the register file. On your machines that are sitting in front of you, that number is more like, tens of picoseconds. So it's, the modern technologies are quite fast in terms of their ability to implement memories and logic gates and things like that. And then here's the information that we have about the write signal. So at the rising edge of the clock, we have both setup and hold time. So we have to have a dynamic discipline associated with the writing into the register file. And we have a write address and write data that we have to supply along with an enable signal. And if the enable signal is high, this data, it will be written into the register whose number is given by the write address at the rising edge of the clock. And we have the usual, it has to be stable for a nanosecond or two before the rising clock edge and a small amount of time after the rising clock edge. And of course, the setup and hold time numbers vary depending on how much money you're spending on your memory and what technology is implemented. A question that comes up that you will probably ask yourselves is, what happens if I have an instruction that looks like this? Say I want to do an add C of R1, I want to add 42 to that, and I want to write it back into R1. Is there a problem if the write address, which is coming from the RC field, so this is the write address, okay, is the same as the read address? And the answer is no. If you think a little bit about how this is working, we can, as soon as the read address is stable, we get the read information out, and that happens very near the beginning of a cycle. As soon as we get the instruction from the memory, we will have the appropriate read address from the right bits of the instruction field. Shortly after that, at a couple nanoseconds or so, we'll get the read information, the register file information out of the register file. We have all cycle to run it through the ALU and add a constant to it. And then at the end of the cycle, we can write it back into some register. Could be the register we're reading out of. And there's no confusion because the write happens right at the rising edge of the clock. So at the beginning of the cycle, we're reading out the old information. And at the end of the cycle, we're writing back in the new information. And it's okay if it turns out to be the same location as before. Okay, so now we get to that sort of by way of introduction, sadly a little longer than one might like, but I think what we'll do now is we can actually start drawing the beta itself, which is sort of more interesting. So what do we need to do to execute an instruction? Well, we need to go figure out where the instruction will come from in main memory. So that's determined by the program counter. So we'll have a special register called the program counter. We'll take the value of the program counter and send it over to the main memory as an address. And the main memory, some number of nanoseconds later, will provide us back the 32-bit instruction that lives at that address. And here we can see a particular 32-bit instruction here. We'll need to look at the opcode bits to figure out what to do. We'll need to be able to read a couple operands from the register file. In this case, we'll need to be able to read R2 and R3. Those are the 2 and 3 here are indicating which register we want to read. We'll need to be able to do an add. And then finally, we need to write the result back into the register file at register 4. So we need basically the hardware to do all of that. Let's start with figuring how we're going to do instruction fetch. This is pretty simple. We have a 32-bit register. Why does it say 00 at the bottom? What is that telling us? Where did that come from? I'm sorry? It's a multiple of 4. So remember that, sadly, we are using byte addressing, even though we're always fetching words, 32-bit words. We actually, so groups of 4 bytes from memory. We always fetch them from a mod 4 boundary, so in other words, 0 mod 4. So we can fetch information from location 0. The next word location in memory has the byte address of 4, and the location after that has the byte address of 8. So the program counter, which is always fetching entire words from memory, or always pointing to entire words in memory, will always have its bottom 2 bits to be 0. So that's that 0, 0 is sort of reminding ourselves of that. So the program counter holds the address of the current instruction in main memory. So we take that output and we simply feed it into the address port of our memory system. So we have a black box, which is takes in an address, and some number of nanoseconds later returns the 32-bit data, which is found at that address. And then we go ahead and use those bits, those 32 bits that come back that represent our instruction. We'll use some of those bits directly as they come back. Well, some of our things like the register numbers we need, those we'll use directly, no processing needed. We can take the actual bits from the instruction and simply feed them to the right wires, for example, in our register file. However, we will take the opcode, the 6-bit opcode, and we're going to run it through this control logic, which is, think of it as just a big read-only memory. It has, well, at least in this diagram, it would have 64 locations because we send in 6 bits. So that's and with 6 bits of information, there are 64 combinations. So depending on which of the 64 opcodes goes into here, we're going to develop a set of control signals. And that'll make more sense in just a second. As you start seeing what the control signals control, I hope all that will be clear. And then finally, as what happens while we're executing the instruction, we're also adding 4 to the program counter. And at the end of the cycle, we will be loading the program counter with the next program counter, the new program counter, which in terms of our very simple execution right at the moment is always the next instruction, that 4 bytes farther along in memory. Is there any questions about sort of the instruction fetch? And we're about ready to fill in all the interesting stuff that actually do the execution of the instruction. Yes?
I'm confused as to why PC is in multiples of 4, and how come the control logic isn't. I thought there were 35 bits sent to the output.
Well, bits 26 to 31 is actually 6 bits. 26, 27, 28, 29, 30, 31. So does that help?
Right, why isn't it 5?
Why isn't it 5?
Yeah.
Oh, you mean, so you're thinking about the control signals that go into the ALU, which were 5 bits of control signal. And those will clearly be information that we're going to have to generate from the 6-bit opcode. Okay, but the opcode in the instruction is not the same thing as the ALU control signals. And we'll discover that the 5 ALU control signals are only some of the control signals that we'll need to generate from the 6-bit opcode. And you would say, well, couldn't we pick a clever encoding so that the 5-bit ALU field was exactly somehow embedded? And we've chosen not to do that, but that's maybe with a cleverer choice of encodings we could have simplified the control logic. I think you'll discover the control logic if you actually didn't implement it as a read-only memory, but instead implemented it as just a bunch of discrete logic. That discrete logic is actually only a handful of logic gates, so it's not very complicated. The transformation from opcode to ALU function code is actually pretty simple. Why is a PC a multiple of 4? So just to reprise our sort of apologia about byte addressing. So we use byte addressing. In other words, we think of each 8-bit quantity in memory as separately addressable. So each one has a unique address. Because we actually are building a memory system that only fetches 32-bit words, the load and store instructions always fetch a 32-bit quantity, we will always be sending over an address that points to the low order of the 4 bytes we want to actually fetch from memory. So we'll always be fetching 4 bytes at a time. And by convention, we always choose to fetch bytes at a 0 mod 4 address. So we'll fetch a word from location 0 and from location 4 and from location 8 and from location C. So I'm just counting up in hex, counting by 4. Any other questions? Yes?
So what's the total size of the memory that we're incrementing by 4 to get through?
Okay, so what's the total size of the memory? Well, we see here that we're actually sending over 32 bits of address. So how many bytes would that be? How many different combinations of address bits are there? 2 to the 32, which is 4 billion. So it's a 4 billion byte memory, or a 1 billion word memory. For many years, that was sort of a very standard sort of size. Almost all the machines that you have now are 64-bit machines, so they can address considerably larger amounts of memory. But for us, we have a very simple machine, so 4 billion bytes is sort of what we can address. Other questions? Okay. Alrighty, so what we have here, we need to put together the hardware that can do this operation. Well, the operation itself is implemented by the ALU you designed. And so we're sort of treating that as a black box. It takes in 2 32-bit operands, and it produces a 32-bit result. That's what you designed. And it takes in a 5-bit opcode. Right, and so part of the job of the control logic is to take the 6-bit instruction opcode, okay, and produce the appropriate 5-bit control signals, the 5 control signals the ALU needs to decide what operation is performing. So we're going to be putting in the 6-bit opcode into the control logic, and we're going to be getting out 2 things, at least so far. One is a 5-bit field, which tells us, which is directly the 5 bits that control what function the ALU computes, and the 6th bit out of the control ROM is an instruction called WRF. You can see the dog here, WRF, WRF. And so you'll never forget WRF once you imagine the little dog barking away. WRF is actually write enable register file. One of the funniest things to do is to get a bunch of engineers in a room who've looked at a schematic, and they've all, sort of anglicized all the names of the signals in the schematic. And of course, people pronounce them differently, right? So how would you pronounce, ALUFN? Alphen, and what happens, everybody chooses a different way of pronouncing it. So you say WRF, and I'm going, what the beans is WRF? And you say, well, that's W-E-R. Oh, that was wee-woof or something, So bear with me. I actually, will have pronunciations for all of these signals, but I'll try to be as clear as possible. Okay, and so you can see that we send the RA and the RB field as addresses into the register file and get out the 2 32-bit operands. Right, so we're sending in 2 5-bit addresses, which selects one of the 32 registers, and what comes out the bottom on the 2 32-bit read ports of the register file are the 32-bit contents of the 2 selected registers. Those become the operands into the ALU. The function that's being performed is determined by the 5-bit ALU function code, which we gave you in Lab 5. You designed hardware that took that 5-bit code and figured out whether it was doing multiply or compare or shifting by a certain amount. And it uses the information it operates on are these 2 32-bit operands. The 32-bit result is fed back into the right data wires of the register file. And at the rising edge of the next clock, assuming WRF is true, which it always will be in this case for all the ALU instructions, we will write the result into whatever 5-bit number appeared in the RC field of the 32-bit instruction. And in fact, if you look at the control ROM diagram, which you can see here at the bottom of your page, what we've basically done is to fill in the first column and the first 2 rows. You can see we're going to have some more control signals and some more instructions to deal with, so the table gets a little bigger. But for now, what we've done is we've talked about the op class of instructions, where the 2 operands come from the register file. And the 2 control signals that our data path needs now are the 5-bit ALU function code and the 1-bit write enable register file. And you can see that the write enable register file, WRF, is always 1, because we always are writing into the register file when we execute this particular class of instructions. Now, we're going to spend, the next 20 minutes adding a few more things, but this data path is, actually remarkably close to where we're going to be at the end. And so this is a good moment to ask any questions you have about this simple version. Yes?
So I understand what happens when work is true, which it mostly is, but what about when it's false?
When it's false, everything works just as it worked before, except that this 32-bit data coming out of the ALU will not be written into any register of the register file.
So it's not safe to put into memory anyway?
If WRF is 0, then the machine will not remember the result the ALU computed. And you'll see that there's exactly one instruction in our entire instruction set that does not write into the register file, and hence WRF is 0. Yes?
Well, I was going to ask, the only one that seems to not be writing is store.
Right, we'll get there. So hold on. It's tempting to run ahead because the story unfolds pretty quickly. But 2 more clicks and I'll be there too. So. Okay, no other questions? Yes?
So the 2 addresses that go into the register file?
Yes, RA and RB fields from the instruction.
Okay, so those are like the A cell and B cell.
In the earlier thing, we called them A cell and B cell. That will turn out to be an unfortunate terminology, as you'll see in just a second. So just think of them as the RA field and the RB field. Okay. Now, let's consider what happens for another whole class of instructions where the second operand doesn't come from the register file, but instead comes from the 16-bit constant encoded in the low-order 16 bits of the instruction down here. So we're no longer treating these bits right up here as the RB field. We're actually using the entire low-order 16 bits of the instruction as a 16-bit number. We have to convert that into a 32-bit number, right? And then we use this multiplexer here to choose whether the second operand into the ALU, the B operand in the ALU, comes from either the output of the register file or the 32-bit constant built from the instruction. Right, so in this case what we've done is we added a new control signal. You can see that in the next line of your diagram here. We've added the B cell control signal. And we've actually set it to 0 when we want to use the second operand from the register file, and we set it to 1 when we want the second operand to come as a 32-bit constant built from the instruction. So we've basically taken care of all but 5 or 6 instructions in the instruction set with this data path. This data path will get the job done. It can operate on 2 register operands, or a register operand and a constant. Let me say a little bit about how we convert the 16-bit number into a 32-bit number. So the 16-bit number in the instruction field is treated, so here's my 16-bit field, so this is 16 bits. This is treated as a 2's complement number, which means, the high order bit here is, if you want to think of that, as the bit that tells us whether the number is positive or negative. If I'm going to convert that into a 32-bit number, how do I do that? Okay, and you can say, is there complicated logic? Turns out it's all just wires. There's nothing fancy here, but we do have to be a little careful about it. So if this number is positive, in other words, the higher order bit is 0, then the 32-bit representation is the same. We just copy over these low 15 bits, and in fact, we copy over that 0, like so. And then we want zeros all the way up in the high 16 bits. Right. So this 32-bit representation is the numeric equivalent. It represents the same integer as this positive number. Right. When this number is negative, what do we do with these high order bits? We make them all 1s. Okay. Because that would be the 32-bit representation of the same integer, right, with a high order bits all 1s. And so the reason it's called SXT is sign extension. This bit here basically gets copied not only to the 16th bit of the constant, but also bits 31 down to 16. So this is bits 15 down to 0, the bottom 16 bits. And so the high order 16 bits are basically the instruction field, number 15, replicated 16 times. So that's sort of the JSIM way of producing 16 bits of signal from a or 16 copies of a particular signal. So that's what sign extension means. Okay, how about the load instruction? Remember what the load instruction does? Well, it uses the ALU. It basically looks like an ADC instruction at some level because it's taking the contents of the RA field and adding the sign extended constant. So if you actually look in the diagram here at the load column, you'll see that it looks a lot like an ADC instruction in the sense that B cell is 1. Okay, and so now what's coming out of the ALU is the contents of RA plus the sign extended constant, but we don't use that answer directly. That is now the address, and you can see we send it over here to the memory, into the address port of the data memory. And so the instruction memory and the data memory are actually the same memory, it's just two separate ports, right? I can ask the memory both for an instruction word using one of its read ports, and on the other port, other read port, I can ask it for a different address. So I can actually, just like the register file had two read ports, main memory has two read ports, one of which is used to fetch instructions, and the other which will read from the same memory array, but usually different addresses, will read a data word out. We'll take this data word, and the data that comes out of memory is then routed through this new multiplexer called the WD cell mux, okay, routed back to the register file, and that becomes the result of the instruction. So if you look here in your control table, you'll just see that we've added a new WD cell control line. The WD cell mux selects from one of three values. From, well, we haven't shown you where value 0 comes from, but when WD cell is 1, we're going to select the ALU output, and when WD cell is 2, we're going to select the data output of memory. And then we're going to route, whichever one of these gets selected by the WD cell signal gets routed back into the register file. And so WD cell would be 2. In other words, we want selecting the 32-bit value coming back from memory, okay, in the case of a load instruction. That's what gets written back into RC. Okay, so what we've really done is to go off and add a data memory so we can read and write into it for loads and store instructions. And we've added this WD cell mux, which allows us to choose either the ALU value or the output of the memory system, of the data memory, to write back into main memory. Yes?
What is 0 do?
I'm sorry, what does? Oh, we haven't, I'll show you in a slide or two what we're going to use it for. It turns out there's one other piece of information that can be written back into the register file, and when we get to jumps and branches, we'll see what that is. Okay, so. Alrighty, so here we have the store instruction. The store instruction is a little weird. It does the same address calculation as the load instruction, and so in fact the data paths that compute the address work just the same as they do for the load instruction. So what's being sent on address wires is the sum of the contents of register A plus the sign extended constant. However, the data that's being written back into the main memory comes from the WRC register. So typically this specified a destination, this field of the instruction specified a destination. In other words, where we're going to write into the register file. But in the case of the store instruction, okay, this is sort of a little messy, but it gets the job done. We reuse that field to indicate what register is supplying the data to be stored into memory. And we don't actually have a way, at least on the previous diagrams, of reading the contents of register C. That particular field was being sent to the write address of the register file. In the case of a store instruction, we're using the RA field, but we're not using the RB field because we're using the B cell as 1. We're using the constant. So we're going to repurpose the second port of the register file, the one that was usually read register B, which we're not using for this instruction. And instead we're going to say, look, for the store instruction, instead of routing the RB field to the second read address port, we're going to route the RC field. So in this case, RA2 cell, which is the control signal for this new mux up at the top here, says either select the RB field or the RC field as the read address for the second register. And then when RA2 cell is 1, we select the RC field. So the contents of register C comes out of RD2, and that's what's sent down here to the read data, to the write data on memory. Everybody sort of happy with that? So you'll puzzle over it. I'll answer some questions in a second. And you can follow along here where we basically have talked now about the first 4 columns in the table. And we're all the way down to the WR signal in terms of control, right? So the WR signal here, this is a write enable for main memory, very much the same way that WRF was the write enable for the register file. The WR signal is the read-write line for main memory. It tells with the memory whether it should only be reading or whether it should be reading, whether it should write at the end of the current cycle. Yes, questions? I saw some hands. I answered the question. Wow. Other questions? Yes?
So WR and WRF are complements of each other for a reason?
They're not, they're independent, right? One is controlling whether we're writing a value into the register file, and the second one is controlling whether we're writing a value into main memory.
But we don't want them to ever both be 1. In the sense we don't want them to write things.
With the instruction set that we have now, we would never expect them both to be 1 at the same time. But that doesn't mean that we couldn't design some new instructions where somehow we were writing both into main memory and into the register file, or something strange. I mean, it's a little hard to see how that would work. But there's nothing at the hardware level that would prevent them both from being 1. It just turns out that with our instruction set, they're never both 1 at the same time. Okay. So now we do the jumps and branches. I hope what you can see here is that we're now going to be fooling around with the PC logic because they affect the program counter. So I'm going to talk about 2 separate things. One is changing the program counter, which up to now has just been incrementing by 4. And the other, and this happens for all the jump and branch instructions, we always into the destination register here, into register RC, we're always restoring the address of the instruction following the jump or branch, so the PC plus 4 value. So PC pointed to the address of the jump or branch instruction, and so PC plus 4 will be the address of the instruction following the jump or branch. That value is the value that actually gets routed through the WD cell mux and is written into the RC register. So in jumps and branches, we're going to change the value of the program counter, and at the same time, we're going to remember where the program counter was before we changed it, where the next instruction would have come from had we not changed the program counter. In the case of a jump instruction, we basically take the contents of the RA register, and that simply becomes the new value of the program counter. So whatever was in the RA register, almost always in our programs, is the value in the LP or the XP register, so the linkage pointer. This is how we return from procedure calls. We basically just stuff that value into the program counter, and away we go. The next instruction will now come from wherever some previous branch came from. Okay, and then finally, branches are very much the same in terms of writing PC plus 4 into the register file, but they need to test the value of RA to determine whether you're going to branch or not. And the choices are, if we don't branch, we're just going to load PC with PC plus 4. So that's what happens if we don't take the branch. If we do take the branch, how do we decide if we take the branch or not? Well, what we're going to do is to look at the value of a particular register and see if it's 0 or not. So we use this big, just like, remember when you put that big NOR 32 on the output of the adder and the ALU to determine whether its answer was 0 or not? Well, we're going to do that same big NOR 32 on the output of register A from the register file. And we're going to test to see whether it's 0 or not. And if it is, we want to set PC cell, as if we're doing like a BEQ. So if Z is 1, in other words, the contents of RA is 0, that means if we're doing a BEQ, if we're going to branch, if it is 0, we basically look at the Z signal to see, is it 0? So that means Z would be 1. And in that particular case, we would set PC cell to 1. So PC, for branch instructions, PC cell will either be 0 if we're not taking the branch, or 1 if we are. If we do select 1, what is the new value of the PC? Well, we take the old value of the program counter, and basically change it by the word offset that's encoded in the literal field. And you'll be talking about how all that works here in section over the next couple days. And so I'm not going to reprise the detail of the word offset calculation, but suffice it to say that this is called a PC relative branch. In other words, some distance from where the PC currently is where the destination is. And that distance, either earlier in the program with a negative offset or farther in the program, later in the program with a positive offset, that offset is added to the program counter and becomes the new program counter. Load relative you'll talk about in section, so I won't talk about it more here. There's one more signal, one more multiplexer that gets added. That allows us to select the output of the branch offset adder and use it as an address. But as I say, you'll chat about that in section. Let me spend the last couple minutes and so that's all we need to do to execute the instructions. There's one other thing that any respectable piece of hardware needs to take care of, and that's dealing with exceptions. What do we do if we run across an instruction we can't execute? Its operation involves either like an illegal opcode. I've looked at the opcode field and it isn't one of the ones that's listed as an instruction. Okay, or I'm dividing by 0, or I'm referencing a non-existent memory location. In other words, it's impossible for the machine to coherently, correctly finish the execution of the instruction. Well, choice 1, a very bad idea, is simply to say, oh, I'll just ignore it. I'll just do whatever happens, and, who cares? It's, the programmer will figure it out. Well, it turns out it's very hard to figure out what goes wrong in a program where the hardware is ignoring all the errors. And you sort of say, well, I don't know. I got the wrong answer, but who knows which of the 12, the preceding 10 billion instructions actually was wrong, was incorrect as an instruction or got an illegal memory reference or something like that. Instead, what we choose to do, option 2, is to interrupt the execution of the program. And by interrupt, we stop execution where it is, and we go off and we run some special piece of software that will deal with whatever the exceptional situation is. So these are called an exception, and we have two types of exceptions. We have synchronous exceptions, which come from the execution of the program, divide by 0 in a legal memory reference. And then we have asynchronous exceptions, and those are, I want you to stop execution of the program, not because the program is wrong, because I have something else I want the computer to work on. Like, I got a new network packet, and I want you to go process that right away. And we'll talk more about this sort of time-sharing aspect of saying, stop what you're doing, we want you to go do something else. So those are so-called asynchronous exceptions. They're both very similar in hardware, as you'll see. We don't have to add a lot to the hardware to make this work, and we're adding pretty much the same thing in both cases. So this distinction between synchronous and asynchronous exceptions will become more apparent when we get to operating systems in a couple weeks. The key is we want to be able to stop execution of the program, but then restart it where we left off if we can figure out how to fix the problem. Or we just want to resume execution of whatever program we interrupted to go deal with network packets. Okay. So the implementation is pretty straightforward. We're going to fake a procedure call. It's just a transfer of control to a special procedure in the operating system that deals with the exceptional situation. And we're going to fake a procedure call, and I'm going to show you how that works now. And so we're going to go off and write, instead of using the linkage pointer, we're going to use a special register, which we call the exception pointer, XP, which is R30. We've reserved R30 for all these weeks and said don't use it, we're going to use it for something special. And the something special we're going to use it for is that's where the hardware is going to stick the value, where the address of the interrupted instruction, actually the PC plus 4 of the interrupted instruction. So for example, if you don't have a divide hardware in your machine, this is an illegal opcode, so when it saw a divide instruction, it would say, oh, I can't execute this. I'm going to go off to this illegal operation handler, and I'm going to basically stop. I'm not going to execute this instruction, and instead I'm going to do a forced procedure call, okay, which is just like a forced branch, where I'm going to save PC plus 4 into the XP register, and then force the PC to the address of the special instruction, of the special code that deals with the exception. And so it turns out all we really need to do is to either recognize, decode that something's an illegal operation in our control logic, or take in an external interrupt signal that says, stop what you're doing, I want you to do something else. In such a case, we choose some special addresses, either hex 4 or hex 8 is the new program counter, depending on which exception we're dealing with, asynchronous or synchronous exceptions. And at the same time, we're going to write the PC plus 4 into the register file, except we're going to do it at R30. So here it says XP, but that's actually the 5-bit number, the 5-bit representation of the number 30. So are we all done? This is the beta. It's actually this like our control logic. We've filled in all the columns. Something that you should become familiar with. You'll certainly learn a lot about it in Lab 6 as you do the implementations. So good luck with that. Typically, we do it with a read-only memory. So that's a sort of a single JSIM component, which you'll learn about when you do Lab 6. Here's our final answer. Regis Philbin would be pleased. Our final answer. Okay, for what the beta looks like. It's actually a remarkably simple little diagram, considering that this is, not too different from most of the machines that you'll meet. The other machines are complex because they're pipelined and they're trying to do high performance, but at the bottom line, they're executing an instruction set which is not all that different from what we're doing today. So is that all there is to building a processor? Well, no, of course you have to do marketing. So we have these little beta inside stickers that you can paste on your lab. So when you check off Lab 6, when you've built your own beta, you'll get your own beta inside sticker, sort of a badge of honor here in 6004. So I look forward to giving you that in lab. Alrighty, good, thank you, and we'll see you in section tomorrow and lecture on Thursday.